the nanomaterial. Although the moderators has introduced my background, but here also would like us to introduce myself a little bit. At this moment, I'm the chairperson at Tsinghua University, also serve as the deans of the Tsinghua International College. This college, actually, we have the different kind of mission. We would like us to recruit the senior high school students to Tsinghua. So that's we would like us to incubate the name from the bachelor degree and names to PhD. So hope that they can learn the more solid the background as well as the advanced knowledge. And at this moment, I also the directors of the Center for Energy and Environmental Research at Tsinghua University, also the conveners of the programs of environmental engineering, Ministry of Science and Technology. This is the government's unit. So that's the now it means that I was in charge of all the environmental engineering programs in Taiwan. At this moment, I also the visiting adjunct professor of Universitas Erlangga in Surabaya. Also, the visiting professors of the University of Shizuoka in Japan. So, get some honors. I think I don't need this to talk about names. I also get some honors and awards that like the chairperson mentioned. Okay, from the 2000s to 2018, they get some domestics as well as some international awards. Okay, and also at this moment, have published more than 200 papers. So from the statistic data, from the Web of Science, my H index is around 49. Per papers has been cited 27 times. Highly cited papers has 3. But when we check is from Google Scholar database, my H index is around 56. I10 is around 139. So that is the background to let you know. Definitely is that the most important is that the research interest here. Like I mentioned, is the topics today is the environment and energy. So that's here would like us to introduce you. That's my background. The first is the environmental nanotechnology. So we'll focus on the remediation or even bioremediation of contaminants in water and wastewater. And we also do some advanced oxidation process, AOP, mainly for photocatalysis. And also would like us to do some to link with energy and names to talk about the capacitive deionization. Also would like us to introduce some material, especially for carbon-based nanomaterial. This is also the main topics that today. I also cooperate with some friends that in no matters in Indonesia or in Malaysia. We are talking about the polymers. So tries to use the polymers for energy application. And for those energy application, many focus on supercapacitor and lithium-ion battery. These two actually now is quite important because for those vehicle cars, also for some other purposes. So the energy storage devices at this moment is very important, and my backgrounds and my research interest will focus on this part. We also do some environmental analytical chemistry very similar to the deans of your college. So the main skills of my research interest in is here. So here we focus on some photocatalysis and for electrocatalysis. So that we call this one is the photoelectrocatalysis, means that PEC. PEC can do a lot of things, especially for water-energy nexus. So going back to our topic, why we want to talk about the energy and environment, because we can talk about the food, water, and energy nexus, or even only focus on energy and water nexus. all these three topics actually is very important worldwide, especially from the UNDP. From UNDP, you will see that in 2016, they launched 17 goals. We call it 17 SDG goals. From these 17 SDG goals, you always will see that the goal 6 and goal 7 is the waters, clean water. Goal 7 is affordable and clean energy. So it means that the environment and energy will become a top issue worldwide during the next 10 years. Because for SDG, till the 2030, the UN hopes that every country can reach the 17 goals. So that's why now, no matter in Asian country or in European country, people are working so hard to fulfill these 17. So that's here you always will see that's the clean energy and affordable clean and waters are the indicators. And this is very important because in Southeast and the South Asian country, we are shortage of energy. We also shortage of clean water. So that's we need to develop very good key technology for environmental sustainability, especially to create clean waters and clean energy here. So the water shortage now is the worldwide problem. So that's here you always will see that when you talk about the water resources in the world, we just think about the whole water resources in the world is just 1 liter. And names in this 1 liter of the water, 97.5% will be in sea waters. And those frozen fresh waters will be around the 2.5%. So 96.5 plus 2.5 equals to 100. And how about the lost available water? Actually, those available water will very, very less, even though just only less than 0.01%. So that's I mentioned that if we think about the whole water in the world is 1 liter, and then the water resources that's available to mankind is only 1 drop. It's only 1 drop. So that means that for this 1 drop of water, and then we need to supply this 1 drop of water to more than 7.5 billion population in the world. So the water shortage actually is very important and is also the big issue in the next 10 years. So that's why we talk about how to use the nanotechnologies to clean or to provide the sufficient water. So carbon-based material is one kind of the solution. Why I focus on the carbon-based material? Because carbon material we have been used for more than 4,000 years in the world. From our ancient times, we have used the coal char, and from coal chars to activate the carbon until now to do the nano-based carbon material. All these actually are all the same. They are all carbon. So they have the very good physical and chemical property, especially their electronic conductivity is good, thermal property is good, chemical stability is also good, density is low, and their availability is also wide. This material actually is quite good, so that we can use this for electron material. So that's why when we talk about the energy application, carbon-based material is one of them. In environments, we usually use the activated carbons as the good adsorbents to remove some pollutants and some metal ions. So that's the carbon-based material actually is very good adsorbents for ion removal, and they also can separate gas, especially carbon dioxide, like a MOF, mental organic framework. Carbon-based material also can use as the support for some good catalysts, for example, platinum and gold. So that's that they can be used for catalysis application. So all these physical chemical property, you always will see that they can have the very wide variety of application, especially in the field of energy, sensing, biomedical, and environment. So why we want to talk about the carbon? Because in addition to their good physical chemical property, they also have the very different morphology from 0 dimension to 3 dimension. So that's the 0 dimensional. The most famous one is carbon-60. Okay, carbon-60 actually is quite well known, and the inventors that has got the Nobel laureates. Yeah. But now we would like us to talk about the carbon dose, graphene content dose, because carbon-60 actually their water solubility is low. So that's very hard for us to be used in environment as well as in energy. But the carbon dose and the graphene content dose, they have some functional groups, and water solubility is relatively good compared to carbon-60. So there's the application is relatively wild in comparison with carbon-60. We also have quite a good image for one-dimensional carbon, like the carbon nanotubes from the 1991. And we also have quite the hard issues, two-dimensional nanomaterial, like the graphene content dose or graphitic carbon nitride here. And a lot of people also focus on three-dimensional. Now, the most famous three-dimensional is the metal organics framework. We call it the MOF. No matter talk about MOF or GIF or the covalent bondings, the frameworks like COV, all belongs to this the three-dimensional carbon. Today we will talk about the highly oldest Mesoporous carbon, and some will be talk about the carbon sponge. So that's the oldest. Actually, you will see that there's illustrations for their structures: 0 dimension, 1 dimension, 2 dimensional, and 3 dimensional here. So how to use this carbon? So that's in 2008, one paper published in ENGWA. They talk about the Mesoporous carbon. So that's here they emphasize the several applications. One is for catalysis. So not just only for catalysis, they also can serve as the catalyst, the support. They can do the separation, gas separation, water purification, or even for the gas chromatography or liquid chromatography, all are possible. And carbon-based materials, since that they are highly older, the Mesoporous, so that they have the photonics behavior and can serve as the photonics materials here. And they also can do the energy conversion and energy storage because they have quite a good electrochemical property. So according to those, there's a good physical chemical property and there's wide availabilities. So that's we would like to talk about the carbon here. Since carbon contains a lot of, so that's today the talk will mainly focus on the graphene family. Graphene family including the graphene oxide, reduced graphene oxide, or even for graphene quantum dots, that's the 0-dimensional graphene family. Has very unique optical and electrochemical property. Yeah, so but for energy and environmental application, we mainly focus on the graphene oxide, reduced graphene oxide, and graphene quantum dots. This especially for the reduced graphene oxide and GQD, because these two material actually they have the very good electrochemical property, conductivity, and names that they can dissolve in water. They have the very limited functional groups, so that will be good. So for electrochemical properties, names they can be used for lithium-ion battery, solar energy, supercapacitor, even for sensing or for catalysis. For optical property, they can be used for sensing and for environmental applications here. So here give you some ideas about this graphene family, even though it is quite popular. Okay, from the left-hand side here, you can see this one is the graphene. Left the no functional groups on the surface, so that's their conductivity is good. So that's you can see that's their electromobility is quite high. But this material cannot be dissolved in waters. They only can dissolve in solvent. It is not as easy to use in our daily life. So that's the people would like us to oxidize them into the graphene oxide. But the problem for graphene oxide is that they have too many functional groups, have a lot of phenolics, hydroxyl, and capacitive group. So that's their electrons mobility is very low. You will see that is quite low here. So that's the people would like us to do it is to use for reduce graphene oxide. So that's they have very less functional groups here. So that will be good. So there's conductivity will be good, and names that there's electronics property will be good, and then they can dissolve in water. So sorry, this two value actually is inverse. For graphene oxide should be insulators. Names for reduced graphene oxide, their electrons mobility should be around 0.05 to 200. Okay, sorry for the mistake. Yeah. So now we talk about some case here. One is the zero-dimensional graphene quantum dots here. So what we want to do this material, we know that the two-dimensional graphene oxides, they have quite a good conductivity, but their optical property is not good enough. So when you narrow down this two-dimensional graphene oxide or reduced graphene oxide, they have just several layers and names into the very, very tiny parts. So they will become the quantum dots. When we talk about the quantum dots, it means that the particle size will be less than 10 nanometers. Betas will be around 5 nanometer. So when all the particle narrow down to the quantum dots behavior, they have quite a unique optical property. So that's from the graphene-based materials to graphene quantum dots, from two-dimensional to zero-dimension. So their electrochemical property will be there because their property is the graphene family. But when you narrow down to quantum dots, their optical property will be enhanced dramatically. So it means that as the zero-dimensional graphene quantum dots, they have the quite unique physical chemical property, especially for optical and electrochemical properties. So we can use this electrochemical and optical properties to do a lot of things. Yeah. And the other case is the three-dimensional graphene family. So from the two-dimensional, since at the edge, they have some functional groups, hydroxyl functional groups or capacitive functional groups, so that they can link together, so that we can try to add some metal ion get inside to the names to link it together. So that's the two-dimensional will become three-dimensional. What we want to do those the three-dimensional from the right-hand side here, you always will see that they have a two-dimensional frame here. So they can keep the electrochemical property of reduced graphene oxide or graphene family. But they have a lot of this space get inside. This space actually they can have some electrolyte get inside. If they have the electrolyte here, named their electrochemical property will be enhanced, especially when they serve as the electromaterials for lithium-ion battery or for supercapacitor. So that's the for three-dimensional graphene family. A lot of people would like us to use them as the very, very novel electromaterial for energy storage and energy conversion. That is the case here. So how to prepare the graphene quantum dots? That's quite simple. You can try to use the top-down methods That means that when you have your graphene family, reduce graphene oxide, some others, names, you can try to use the physical methods just to grind, to chop them into the quantum dots. That's the physical method from top down. And from the bottom up, you can try to use the chemicals to do. For me, I prefer to use the chemical method. The chemical method, actually, we can fabricate quite a nice and quite uniform the particle size. Okay, so we can do the pyrolysis of the citric acid or other carbon materials. So that's here is one kind of the citric acid. Citric acid has the 3 carbon, 1, 2, 3. So that's if they have the 2 citric acid names that they can form the benzene-like structure. So that's they are quite easy to form, the 0-dimension graphene quantum dot. So that's we just use the temperature as the 200 degrees C, 25 minutes, and names that they can form. Here you can see that's when you irradiate the UV light at the 360, they can emit the wavelength at around 460. So that's their fluorescence property will be good. And we can do the surface modification so that they can do a lot of optical and electrochemical property. If you do not have the citric acid or the other carbon materials on your hand, that will be also quite easy. We can buy some carbon-based raw materials from the market. So that's every country has the agricultural waste, like the passion fruits, like coconut juice, like apple juice, or the citron. All this actually contains a lot of citric acid and some sugars, glucose and some others. So that's for example, in my lab, I just used the passion fruits and put some boric acid and names that's just to get rid of the seeds of the passion fruit, have their juice here, and put the boric acid get inside. Still use the microwave 170, 20 minutes, and names we can get the graphene quantum dots. If you ask that the boric acid get inside, you can get the boron-doped graphene quantum dots. And for those natural products, most of them contains the nitrogen. So that's when you use the natural products that's to fabricate your graphene quantum dots, you always can get the nitrogen doped. Since you have the nitrogen doped, so that's their electron density will enhance dramatically. So that's their quantum efficiency will be good, and names that their electrochemical conductivity will be good. So that's we can use this for the paper strip the sensors to detect the tetracycline or some other, and also we can decompose them. So that is quite simple. So the preparation methods of the graphene quantum dots is quite simple, so that we can use this material for a wide variety of applications. So that from now on, I would like us to introduce you how to use the graphene quantum dots for application in environment and energy. Here is their physical chemical property and their morphology here. From the passion fruits, okay, yeah, from the natural carbon, we can get the quantum dots here. So that's here is the case. So that's when you see the blue colors, that's the graphene quantum dots. When you use the atomic force microscopes to see the topography and to do the thickness of the lost carbon-based material, here you can see that's their thickness only around 2 nanometers. 1 layer of the carbon is around 0.334 nanometers. If you ask the graphene oxide will be around 0.8 nanometer. So that's 2 nanometer means that they only have the few layers of this carbon. Since there are only few layers, so that's we can make sure it's a graphene quantum dots and not the carbon dots. On figure C, we'll see their particle size from the TM, so that's their particle size at around 9 nanometers. Names here is also the case, so that's I don't want to go in detail. So that's for this GQD, you can do the energy application first. So that's the since the GQD is the zero dimension. So that's the particle size only for around 5 to 10 nanometer. It is very hard to see and to separate. So most of the time, we will use the zero-dimensional graphene quantum dots with some support. And here we select the one natural occurrence materials as their support. We call this one is halloysite nanotube. Halloysite nanotubes is the naturally occurring layers clay mineral. We can find these materials in soil. So the characteristic of this material actually they contains the aluminum oxide inside on the inner surface, and they have the silicon dioxide on the outer part. And from the soil chemistry, you always will know that since the layers do the balance. So alumina is the 3+, silicon is the 4+. So when they maintains in the same material, so most of the time, your silicons will become negatively charged, and your aluminums will become the positive charged. So this material actually has been widely used to absorb the metal ions in soil. So that's quite common. But now we use this for energy application. Since their outside is the negatively charged, inside is the positive charge. So that's we can try to let the electron get inside. So they can store some energy here. And then we put the graphene quantum dots on the surface. So that's here is the case. Sorry. So that's here is the case. When we put the graphene quantum dots on the surface and then tries to do the surface modification, and then we can see this one is the halloysite nanotube. Do the test for surface modification, and then we can get some good absorption abilities on GQD, so that we can put it. If you would like us to recover or enhance their property names, that you can add some metal oxide, for example, like iron oxide or some other. So here is the case. I just very briefly and very quickly to see that we still can see a lot of the graphene quantum dots. Names that this spacing is the 0.21, very close to the carbon. Okay, and their particle size is around 9, very similar to the GQD we fabricate from passion fruits, and then you can see that they have quite a good optical property. And then when we put the epitaxy on the surface, the names outside, this outside actually is the epitaxy. When we enlarge it, we can see some spot. This one is the graphene quantum dots here, so that we can see the case. So here we always will see their microstructures here, including SPS, XRD, BET surface area, and the thermal property here. I don't want to go detail. If you are interested in that, you can read my paper. We have published this one in 2008. I'm sorry, 2018. Okay, yeah. Names that the electrochemical performance here, you will see that they are quite rectangular. It means that the graphene quantum dots plays a very important role here. Names that their behavior is the ideals, EDLC, electric double layers capacitance behavior. And here we also can see the quite a good triangle. So that's you will always will see there's capacitance can be around the 320 farad per gram. Actually, this value is quite high. Named that their cycle numbers can be up to around 5,000 times, can maintain around 87%. So that will be also quite good. So that's from here. So we also can get this. If you have the iron oxide to get inside, the value will increase a little bit because you add some metal oxides, so that their value will be increased a little bit, but may not be good for their energy density and power density. Here is the case for energy density and power density. Here you always will see that when we only have the GQD HNT, their power density actually will be high, but their energy density only around the 30 to 50 watt-hours per kilogram. When we ask the iron oxide, their energy density decreased a little bit from 29 to 10.4. The reason is that we count the energy density and power density by weight. And for HNT and GQD, actually they has quite light. So that's to every kilograms that they can have the more GQD on the surface. So that's their power density is high. Since iron oxide is much heavier than GQD, so that's even though their capacitance is high, but their energy density decreased a little bit. But you always will see that the no matters we ask that the iron oxide inside or not, their value will be good. For this plot, we call this one is the Ragone plot. Theoretically, my goal is to try to have our power density higher than 100. And our energy density will be higher than 10 or even 100. So that's the my goals in my lab. Actually, we just have the 100 the rules. So that is the case here. But now the power density is quite easy to get 10. Names that the energy density will quite easy to get around 50. So it means that there's not just only for supercapacitor and battery. There's we call this one is the supercapacitive battery. Means that they have the very high power density as well as they also have very good energy density. In the next 10 years, we hope that we can get this Ragone process to this region. Okay, so that's their value can around 100 and 100. In that case, names the material can be used in real industry. That's the case. Not just only for halloysite nanotube, you still can immobilize the GQD on the surface of two-dimensional. For example, VNS here, vanadium dioxide nanosheet. So that's here is the box V205. We try to use the hydrothermal methods to separate the box of V205 into the layer 1. And then we put the GQDs on the surface of our VNS. So that's we call it the VNS GQD. Here we do not use the citric acid or some sugar. We use the pyrene. So that's the pyrene will be quite easy to form GQD and their surface will be relatively high. And then we try to fabricate our negative electrode. We use the carbon cross and then put some three-dimensional. We call this one is the Mesoporous carbon field. You will see their morphology here. So that's the one electrode used is the VNS with graphene oxide. The graphene quantum dots. And names that the other electrode we use is the Mesoporous carbon field. So we merge them together. So we call this one is the asymmetric supercapacitance. Okay, yeah. So their value will be here. This one actually is the case with the VNS and graphene quantum dots. The upper part here. The lower part is another case. We call this one is the MCS Mesoporous carbon field. So that we can see the field here. And then from the TM, we can see they have some nice spot here. This one is their pole here. So that's here we can see the low angle XRD and names that they are quite good. And names from the Raman spectroscopy, we also can see the D and G band here. So that's we use these two together and their electrodes property will be good. Here is the case we have the VNS GQD. The value can be around the 550 Faraday per gram. And if we have the Mesoporous carbon names, their value will also around the 550. So from anodes, their value will be around the 550. From cathodes, there's a capacitance will around 550. So that it means that this value will be quite close. And then when you merge them together here, when you merge them together, names that they can have the very good efficiency here. So that's when you use the MC as the negative electrode here. So that you can see that their potential is negative. When you use the vanadium dioxide with the GQD, names that the weight percentage is 10, they can serve as the anodes. So that you can see that the potential is positive. So that's the behaviors will be quite good here. And there's a potential will around from 0 to 1.5. So that's quite a large. So that's in that case, we can get the Ragone plus is here. So that's I mentioned that our value is 100 and 100, and that is the goal to here. But at this moment, our value is the larger than 10 and 10. That's the essentials for electrode material. So our value actually is relatively high compared to the now reported data here. You always will see their value is here. So it means that when you use the graphene quantum dots with carbon with some other carbon-based material, there's energy and power densities will be relatively high here. So you always will see that there's the retention will be also good after 5,000 cycles. That means that the discharge will be good. Here we analyze the contribution of the diffusion and capacitive. We always will see that when you use the high scan rate, the capacitive contribution will be much higher. Means that the GQD actually play a very important role here. So not just only for energy application, you also can use these materials for capacitive deionization for environmental application. The same ideas is the same. Capacitive deionization actually is the capacitive deionization, their principle is very similar to supercapacitor. They just store the electron get inside, and then we just change the electron into those ions, sodium ion and chloride. Yeah. So the principle is the same. So that's here we always will see that we just use the graphene quantum dots with halloysite nanotube. Hope that you remember that we use this material for supercapacitors. Okay, yeah, and here we use the same material but just add one nitrogen dopant here, and names that to use the capacitive deionization. So that's we just apply some brown waters or gray waters to get inside. They contain some contaminants and ions get inside. When they pass through the cells, and names all the ions will be removed. So that's that they absorb on the surface here, and only water molecules can penetrate. So that's after the treatments here, you always will see that's from the contaminants that contain some impurity here. Color is pink, and names becomes the blue, means that's the colors of pure water molecule here, and names we can do it so that we can get the desalinated water here. So the concept is very simple. And all the physical chemical properties will be the same as the data I mentioned, but we use it for removal of ion. Here you always will see when you change the flow rates and the names that the potential and the concentrations of our ion, we can get different kinds of the Ragone plot here. This one is the specific electron capacitance. This one is the specific electron absorption rate. So we call this one is the CDI Ragone plot. This CDI Ragone plot, you always will see that the value is quite good. So that's when you compare our work with some other good material, like even though for MOF here, for carbon bond, three-dimensional activated carbon, This material actually is quite good compared to low carbon-based or some advanced material here. So that is quite good here. We published this just in these years, okay, in Environmental Science Nano. And for GQD, they are not just only for energy and environmental application. We still can use this for some other possible application. If you are not in the field of environment and energy, you still can be used for sensing, for analytical chemistry, or for biomedical application, or even for upconversion for photoelectrochemical application. So just to give you some example, we published these ideas in Science Report in 2019. We tried to immobilize the GQD and SGQD on the penny. Penny is one kind of the conductive polymer. So that's we used aniline as the monomer, and then tries to immobilize into tries to fabricate into the polyaniline, we call penny. We put the gold on the surface actually, so that you can see the gold here. Names puts the NSGQD here. So that's the names immobilize these materials on the surface of electro, platinum, and some others. So when we enlarge the names, we can see that this one actually is the penny, okay, quite good, one-dimensional. When you put the gold on the surface and names, you always will see that they have some spot here. This spot is the gold nanoparticle. And names we use this to put the NSGQD and put the anti-CA antibody and names to detect the CA. So the biomarker actually is not the good conductive material, but GQD and gold and penny are all good electroactive material. So that's their conductivity will be low. So that's when their conductivity will be low, their impedance, this diameter will be low. When you push the CA, it's not the good conductive material, so that's their impedance increase dramatically. So that's from the diameters of this impedance, we can get their calibration curve here. So that's we can get the kind of good calibration curve here, and names we can get the numbers of the CA. We still can use this carbon dose or graphene quantum dose, the names to detect copper, or use some antibiotics like a CIP. So that's you can see that's when you use the graphene quantum dose to detect the copper, their detection limit will around 4.8 ppb. This value actually is more sensitive than name AAS, okay, and very close to ICP OES. So that is quite good. And we also can use this to detect the CIP, a kind of whilst use the antibiotics for our food. Okay, so that's you can see, and their sensitivity is also good. So all this actually just to let you know that the graphene quantum dots actually can do a lot of things. Oh, okay, forgot to mention, we just published this papers last month. Okay, yeah. Okay, and you also can use this to detect some environmental pollutant like the 4-nitrophenol. So that's we use the citric acid and some sulfurs salts, mercaptose propionic acid, and then tries to do it. And then we put the gold precursor get inside. Since your GQD is the reducing agent, so that they can reduce your gold ion into gold nanoparticle, so that we will get the gold GQD, and then we can use this to decompose nitrophenol as well as to detect nitrophenol. So their efficiency is also quite good. We published this 2 years ago. You also can use the GQDs, names use the name added with beta cyclodextrins to detect the cholesterol. So that's here is the case. You can use the GQD, and name has the beta cyclotetrane, a name there on the surface, a names if you have your ferric cyanide, a names that they can be here. If you have the cholesterol, they can get inside your cyclotetrane, a names that replace the ferric cyanide. So that's the peaks, the electrochemical properties will enhance dramatically. So that's from these electrochemical properties, we can detect the cholesterol quite easy. You also can use it for upconversion. Upconversion is quite new at this moment. We always know that the graphene quantum dots that they can do the Doong convergence. The optical property means that we use the low wavelength 360 names that they can emit the 440 or 460 nanometer. So that will be the case people would like to use. But the one characteristics of GQD is that they have the upconvergence property. So that's when you use the long wavelengths like 730 names, they still can emit the wavelengths at around the 440 nanometer. What's the advantage for them? Just think about that we have the solar energy. For those the solar energy, people would like us to use the visible light, even though for IR region, so that they can enhance there's light penetration and the light harvest efficiency. But it seems quite hard for us at this moment just to use the long visible light near IR range. So if you add the upconvergent GQD get inside, names they can use the long visible light 730 or even to 900 nanometers. So they can recover the low light and names that your solar energy become more efficient. So that is the case. We try to develop the low upconverging case. So that's for GQD. They are not just only to receive the UV light, they also can receive the long visible light. So that they can do the same way simultaneously. So that is the good way. So that's the principle is here. Okay, yeah, but since time is very limited, I don't want to go in detail because I just finished a half, so that I need to finish as soon as possible. So that's the names that we can also use the two-dimensional reduced graphene oxide for energy and environmental application. So this one actually is the case for graphene in reduced graphene oxide. So that we can see the sheet here. The surface areas is here around the 44 and then 570 is relatively high. We immobilize some metals on the surface of reduced graphene oxide and names you can see that they can surface very good. So when we use this one, this covers image to tell you that when you have some contaminated water, you can see that the color is brown. Okay, the color is brown. When they pass through the reduced graphene oxide, immobilize some metallics, some metals, the color will be clean. Okay, so the case is quite simple. We just use the boron copies, the reduced graphene oxide, and then put the iron nickel, and then they will reduce this to the zero valence, the iron and nickel. So that's here is the case here. So we use this to decompose the trichloroethylene, some chlorinated compound. So that's just only around 20 minutes. All the chlorinated compounds can be decomposed, and then they will convert into ethane. So that will be good for them. Yeah. So here is the case when we use the reduced graphene oxide or boron copies the reduced graphene oxide. The case will be here, and we also can use this to remove some metal ion like coppers here. So that will be the case here. We can do. We also can use these materials for CDI, like I mentioned. If you put the MnO2 on the surface of the nitrogen doped RGO, names, you can see that they can remove the NaCl. They also can remove some pollutant like microcystine and some coppers here. So all the case is possible. You also can try to use some metal oxide, get inside and names to do the CDI here. Okay, graphite and names to remove to merge with our MnO here. And names use the hydrothermal methods and names to coat it on the surface of titanium plate. And name there forms our materials for CDI. So that's from these ways, you always will see that they can try to remove some ion, especially for high concentration of NaCl, and names that they can get the clean water. Okay, so the final part I would like us to introduce is the three-dimensional highly ordered mesoporous carbon. Here is the case we can try to do highly ordered mesoporous carbons. Originally, they are similar to this one, like a sugar. But when you do the carbonization, they'll become here. So that's here you can see that we can see the black colors. The black color is carbon. We can see the white color, quite the good highly ordered. Okay, this one is their whole. So that when you get enlarged name, use the high resolution TM, we can see that their strict is here, a name get inside from the high resolution TM. We can see the pole here. So that's you can see that's the arrangements of the pole is quite homogeneous. Yeah. Okay, so that we call this one is the highly ordered. You can put any kinds of the metal oxide get inside TiO2, ZnO2, and ZnO, and some others. So that we always can see here. So that we use this for lithium battery. So we have the highly ordered here, but they have the pole. So that the lithium can store in their pole. So that's when you do the discharge, the lithium ions will be get inside and get outside here. So that's that they can get inside the TiO2 here, also get inside the carbon. We can put the MnO2 get inside here, and names you always will see here. Use the EDS mapping, use the highly ordered mesoporous with MnO2. Then when we add the 5.4% of MnO2, their case is here. 8.9 is here. 12.8% of MnO2 is here. You always will see that carbon, oxygen, and mechanisms are all the same. Names also use to just 100 milligrams of the methylene group, so that they can remove in 2 hours. So that's the efficiency quite good. You can see that the absorbed amount is almost 100 of milligram per liter, means that that's all can be removed. We can use this one for lithium batteries. I don't like to introduce this in detail, but you always will see that the value will be good. So that you can see it when we use the asymmetric one, there's potential window can be around 2.2. So that's that their value will be high. So just remember, I mentioned that our goal is here, 100 and 100 to this region, but now you can try to see that's the 10 to 10, okay? 10 to 10 can publish your result in a very good journal. If you can guess 100 to 100, maybe you can publish your papers in Andvances, in Hsince, and Nature. Yeah, okay, yeah. So we also try to use the Mesoporous carbon spheres. We mentioned it previously, so that's I would like us to do it very quickly. So we put the tin oxide on the surface. Okay, so that's the outside. Actually, here is the tin oxide, the black one. So that's you can see that's when we use the line profile. This one actually is the carbon. This one actually is the tin. So that's the inside. There's the no tin get inside, but outside we can see that they have the high concentration of the tin. So that it means that the tin is just go outside. We use this for low good lithium batteries as application. So that's our value is here. So that's you always will see that's the much higher named the reported data. We also use the three-dimensional force CPI. This one is their morphology here. Their pole is high. Okay, so that's their pole is high. So that's the penetration will be good. So the SEM image here, you can see that we have the lot of pole get inside. So that's the water penetration, electrolyte penetration will be good. A names that there was high surface area, so that's ion as well as electron can be absorbed or removed very, very fast. So that's what we use is the force ratio, only force ratio compared to some other activated CNT and some others. You will see that's the value. Finally, I would use the raw the three-dimensional carbon. This one actually is very important ways. Actually, a lot of different kinds of agriculture from different countries, and this the cost benefit. And most important is that that's the use of these agricultural ways to fabricate three-dimensional carbon is the world trend, especially for circular economy. That also one kind of the very important principle. Has to use that, for example, the cone leaf, okay, coffee bean grounds, or use the sugarcane bagasse. Names we can grind names that to fabricate very simply to form the carbon. Names to form the supercapacitor or the CTI or some biochar. So that's what we just use this very simply grind and name carbonization for 54 hours activate to do the as we'll see, they will have the some residue here. They are from coke. This one may not be good, but their surface area will be high. So that when we use the coffee bean, yeah, so the activity is the temperature is the 850, and then the surface area will be around 3,000. That's very, very high, very, very high. And then there's electrochemical property will be good. So that's the here you always will see. We can up to around 100, but unfortunately that there's only around the 30. So that's our goal is tries to move these ones to here, so that they can around the 100 and 100. So that's our goal. You also can use the coconut shells to do it. And for CTI, we just published this in desalination this year. And you also can use the sugarcane bagasse as the scaffolds to immobilize the highly odorous mesoporous carbon. So all these actually are possible. All these are possible. So that is the case. So finally, I would like us to introduce some idea. Here we do not talk about the conclusion, because for nanotechnology we do not have conclusion. We only have the opportunity. The opportunity is that we can try to fabricate the multifunctional composite and use the carbon as the support. So that you can try to fabricate the various materials on graphene or some carbon-based materials to induce more function. You can immobilize with biomolecule or so nanoscale objects or polymers. Names you can try to do the water-energy nexus. Here you can put the porous carbon here and name immobilize your metal oxide. Here is one carton here you can see. If you have the highly porous carbon here, they can do the capacitive deionization, supercapacitor lithium battery for energy. You have the metal. Metal can do the reduction part. You have the metal oxide like a TiO2. You can do the ALP oxidation part. And then you can merge all the function meters in chemistry, in environments, in biomedical, as well as in energy together, do the energy CTI reduction oxidation together, and then you can apply no meter for water treatment technology for energy. That will be good. Okay, so that's the talks of my today. Thank you, and also would like us to thank my lovely students and financial support from the most of Taiwan. Thank you.
Okay, thank you, Professor Ruey and Doong. I think that is, thank you very much for transferring the interesting and the interesting topic for us. And we have collected some questions, and we have 3 questions, Professor.
Yeah.
Okay, wait, I will share some.